morning. Quick introduction. I'm Professor Eyad Masad. I'm with Texas A&M University in College Station, Texas. And we have a branch campus in Qatar. I'm associated with that campus as well. And I'm the Executive Director for Global Partnerships for the Texas A&M Engineering. And I have to confess to you that I always give presentations, whether to my students or to conferences, about things that I have done, and I'm reporting results, recommendations. I don't recall when was the last time that I gave a presentation like this about something that I want to do. So bear with me, and I appreciate your patience. I've been studying this topic just in the past few months. Of course, I'm on this side. I'm a material engineer, civil engineer, trained as a civil engineer. I work in materials characterization, materials modeling, developing materials, but I never worked in artificial intelligence. So I've been studying it very hard. So for those students, although I'm been teaching for many years, I've actually been reading a lot of papers on this topic because it's a topic that interests me and I want to get into that field. So I'm going to tell you what I learned in the past few months. And I want to acknowledge my student, Muhammad Jarrah, graduated from Jordan University of Science and Technology. He joined me as a PhD student recently, and he helped me a lot in the brainstorming and developing the presentation. The main issue is, I'm going to tell you today about what are the challenges and drawbacks of conventional methods in material science. So basically, I'm going to tell you about what things that challenge me as a material engineer for the past 25 years working in this field, and how I see that AI could be a solution for some of these challenges. Not all these challenges, some of these challenges. So what we are trying to do in machine learning and material science, we're going to talk about how did it progress recently, how can we use it to predict material behavior, which is a big issue for us, is to understand how these materials will behave under different conditions, whether they are environmental conditions, loading conditions, so on and so forth. And maybe the most important thing, how can AI help us to design and discover new materials, which is a big goal in material science. And then I'll reflect on what are the pros and cons of machine learning in material science and what are the future opportunities. These are the references that I've been reading in the past few months. And you can see a lot of it has to do with industrial waste, designing new materials, developing database of materials, and you will see why that's so important to properties. A lot of it from China, United States, and so on and so forth. More and more references on this topic. What's interesting, I did a look in the Web of Science. Web of Science is a credible database for looking at what's published out there. And I restricted my search from 2015 till recently. And you can see how significant it is, the growth in use of AI. So what I searched for artificial intelligence with material science or material design. And you see how the curve is growing. Look at citation. From 2016, you had less than teens citation, 15, 17, so on and so forth. And now in 3 years, we have 280 citations on this topic. So I felt like maybe I'm getting into the right field or shifting my interest towards the right field because it seems that's growing rather quickly. Why there is an opportunity? We have been privileged, the advantage that we've seen recently, a lot of the tools we use in material science generate huge amount of data, and I can tell you that I think we benefit only from maybe 10-20% of this data. For two reasons. Our capacity, computational capacity to utilize this data is limited. Our ability to extract data statistically is limited. Give you examples from my own research. This is an atomic force microscopy image, 10 microns. In fact, that's considered a big image, but that was what was on my computer to put in the presentation. the resolution of every data point in that image is in few nanometers. This is an image, believe it or not, of asphalt, liquid. I could not imagine 10 years ago that you can see that level of detail in an asphalt image and know what's happening inside that material. But when my students, my PhD students, work on extracting data from it, we extract 2-3 parameters. So we're missing a lot of data that we don't know how to extract. This is another amazing capability, which is to do 3D imaging of materials. Just like, God forbids, when you go to the hospital and they put you in the machine, not MRI, to do CAT scan. Here we are doing CAT scan for engineering materials rather than human body. The amount of data, in fact, my PhD student recently, Malik, came to me and said, every computer I try to use in this university is crashing when I input my data, which is true. So I bought him another machine. I think he was just tricking me to buy him another machine. So its amount of data we're generating is huge. And I don't think we're getting the best out of it. It's like investing $1 million on something and then you use $1,000 worth of it. So I'm gonna work with, see if AI is an opportunity. What is the challenge in material science? The biggest challenge with material science is the time it takes from discovery of a new material to usability of that material deployment is 10 to 20 years. A lot of time goes between the time you discover to the time you deploy a material. In fact, what's not in this graph is the time it takes to discover, which could be decades to discover that material. It's also becoming vital to develop new methods for accelerating the discovery. So we must shrink that scale to less time. So how do we shrink it? As you know, AI, now you're being in this conference, that it has huge capabilities to do a lot of calculations and extract a lot of information. So hopefully that scale will shrink. And material behavior prediction is very, very challenging. So if you give me a new material, I'm a civil engineer, so the type of materials I work with is a granular material, soils, road materials, composites. And if you give me a material and say, how would this material behave under certain condition, it's very challenging for me to simulate these conditions. I mean, I can simulate UV light, I can simulate moisture, I can simulate loading, but it's very challenging for me to shrink the effect of time, to look at how the material is going to behave under years of service. So can AI help us in this domain? Recently, materials design discovery using machine learning has shown impressive progress. So there is progress. From the papers I've been looking at, there's good indication that this could be good progress. Now here, I'm gonna criticize what I do. So what I do lab experiments and I do computational simulation. In fact, it's very hard for me to criticize because all of my other presentations is I advocate for how good these things are. But the truth is, lab experiments could be time consuming. You need resources. Sometimes it's available, sometimes not. I believe we have reasonable prediction of properties. So you give me a material, I can predict the property, but we are extremely limited in predicting ability to simulate what's going to happen to this material under normal conditions. And of course, subject to human errors, which is not a big deal. I mean, that's okay. We can even predict how much the human error from repeatability and reproducibility. But this is, I believe, is the biggest issue. I need to figure out this thing. Okay, so the pointer is the top one. I have to say it to remember it. Okay, computational simulation, which is augment lab experiments, has a lot of great advantages, but has also disadvantages. What you get in is what you get out. So the assumptions you make in your computational model dictate what you get out of it, right? You get what you assume things, the output is reflected by these assumptions. And of course, depends on the microstructure, which is hard to simulate. Now it's not so hard nowadays because we have this computational power. It's very limited in looking at time and exposure conditions also. And no explicit use can be made of previous calculation results when a new system is studied. So I mean, this is not completely true, but it has some truth, that when you do a new system, you have to make a new model. So what made the progression in the last 10 years? There have been a lot of progress that's encouraging the use of AI. Launching of the Materials Genome Initiative, I'll tell you more about it, which is basically a huge database managed by National Institute of Standards and Technology in Maryland, United States. Emerging of big data era, a lot of data coming, as I told you, because of the machines we use. A lot of data sets are being developed because with these data sets you can do very little. In fact, the biggest challenge I have, I see where AI can help us in our research to predict material behavior. I honestly don't know where I'm gonna get the data to train this AI, useful data. A lot of my colleagues in China and United States collecting data similar to what I collect, but they don't collect it in the same way we do. They don't store data in the same way. And the machine learning algorithms are used to predict material behavior and to design and discover new materials. So there's some evidence that this can happen. This is the progression in the last 10 years. I'm going to give you an example, the Genome Initiative. It's a multi-agency initiative that combines artificial intelligence and machine learning techniques with the best ideas from the world of material science. So they are looking at this initiative, which is 2011, so it's not so recent, that looks at how do we combine computational methods with experimental methods and with data in various applications. And how will this work? Basically, I mean, if you attended any of the sessions, you already know this, is you get the original data, and you sample it based on features that you believe will correlate with your models. You develop these black boxes, and then from these black boxes, you predict the knowledge, and these black boxes get trained. And I underline black box. Underline black box. You'll hear me more talking about it more. I cannot even comprehend how I will advocate, unless I completely change myself, to a field in which the prediction is based on a black box. Because I work with physics, I work with thermodynamics. Honestly, it's almost threatening to me because I feel like everything I learned, this may tell me it doesn't matter. Physics, thermodynamics, chemistry. I will show you hope later that this might not be true. But if I believe completely in the black box, meaning the data will come in, it will train, and then output will come out, and the physics and thermodynamics and the chemistry that I have pride myself of knowing and predicting based on it might be of less value. Right? Because you don't see anything here in physics and chemistry and thermodynamics. So in material science, what has been used, ML, machine learning, it has been used in applications that have been used in property prediction. This is actually easy, how to predict property. It's not difficult whether it's machine learning or with testing or with computational tools. Materials discovery, huge opportunity, I think, in ML. How do you accelerate discovering new materials? Let me tell you the idea in this literature, what it is. How do you discover new materials? It needs a lot of chemistry intuition and knowing the fundamentals. How AI can help you to know if you have a data set in which this data set is a material composed of different elements. Let's simplify it. And you know the properties of this composition. So if you say, this composition give me this property, this composition give me this property, let's say you have 1,000 of these results. Do you imagine the opportunity now in which you feed this data to a machine learning system, it learns relationship between composition and property in a way that you cannot really discover one-to-one in a linear or nonlinear fashion. And now you say, give me materials the material composition that will satisfy this, and this property. So you are discovering a new material without testing it, based on data you collected in the past. Is this clear? I mean, that's the biggest opportunity now in material science. And some people who are less optimistic say, you actually don't need to design a new material. it's enough, which I agree, to narrow down your options of new materials. So instead of having 10,000 combinations you want to experiment in the lab, now you have 100 combinations you want to experiment in the lab, because machine learning will tell you, based on the data you gave me, if you want this property, this is potential compositions. Huge opportunity in that respect. I just told you about this, prediction of material behavior. And the examples are amazing. There are examples on properties of roads, geopolymers, reinforced concrete, copper, plastic deformation copper, organic compounds. So been a lot of applications who are doing it. I talked about this, which is, and if you want to take anything from my talk, the most today, I might contradict myself after I read more, or I find that's going to threaten my existence as a professor of chemistry and physics, then I will quit it. I will just do what I do for the next 10, 15 years till I retire and let my children take over these things instead of me. But we'll see. I may take this challenge. Now what we do is elemental alteration and structural transformation. So how do you design new material? You look at change the structure of the material and you change its composition, right? AI can do this for you if you train it with a certain set. So that's, I think, the biggest opportunity we have. Because of sake of time, I will go a little faster. This is just examples of material discoveries that are in the literature. So you are welcome to look at the references that I put here if you want to read more about it. So they've been discovering new materials, oxide compounds, polyethylene composites, and new materials that are being discovered with the aid of machine learning. Pros and cons of these models. The pros, let's start with the pros. Let's start with the optimistic side. Can be used to complement experimental design. As I just said, narrow down which one you want to take to the lab. Instead of taking to the lab 1,000 materials, you go to the lab with 10 materials. A quick prototyping, models can be created without sophisticated mathematical derivations. You see this? I want the sophisticated mathematical derivation. You know why? Why do I want the model? It's not exact. Actually, it's a model. All models are wrong. Some of them are useful. Close enough? In fact, I think the biggest thing why I need these models, I want to examine it. I want to convince my own neurons, that this makes sense. In the black box, I have to have faith. It's almost like religion to me. I mean, you have faith in it. Instead of examining, you examine with faith, but up to a limit. With this one, you really cannot examine a lot. There's a lot of emphasis now in developing models for validation, verification of these black boxes. So now they call them white boxes. So what are the white boxes? I'll tell you a little bit about it. The learning progress can be guided by introducing experts' knowledge. That's almost going from black to gray. And some people may like this, some people will not like it, because I like it. I like that, to guide the development with my knowledge. Some people will say, your knowledge is limiting what the material may do, because your knowledge is not absolute too. So my knowledge might put boundary condition of what I can discover. But I'm willing to live with that rather than let it completely be black box, because I want to verify it. And of course, now you can predict based on basic inputs. You don't need a lot of inputs. You just need composition and structure, elemental composition and structure, some basic input on properties. You can narrow down these materials. The cons, the biggest one is the ones in red. It's a black box. Some of them are black boxes, data in. They do the training and you get the output. White box models often compromise the prediction. That's what I was telling you. So on the pro side, yes, white box give you the physics. So basically, you know what a white box is. You tell the model, predict the outcome with me, but it must obey 1, 2, 3. Or the model should include parameter 1, parameter 2, parameter 3, parameter 4. And you can even make it more. It should predict it, the behavior, with these parameters, and the function should look something like this, based on physics. So I'm limiting what it can predict. To me, I'm limiting it to obey physics law. To some people, no, you are restricting what the model can tell you. You don't want to face the truth. What can tell you? I hope I'm not confusing with that, because this is what goes in my head when I goes in it. So that's really the big issue. I think it is, but there are two big issues in application of AI in material science. One, you go home with this, is the black box threat and how to convert to a white box without limiting the data. Second, where is the data? In many fields, in my field, I have to generate the data or collaborate with a huge group of people, which we may, to generate the data, but you have to generate it according to specific formats, specific requirements, specific protocols, because we are not so good in comparing our protocols with each other. I may collecting the data different protocol than another person collecting the data. Future opportunities. Creating data is a huge opportunity, and in fact, in itself is an opportunity, because we don't have all this data. And there's no evidence, I believe in this, although I spent all my career developing these models, that mechanistic models are absolutely optimal. So who to say that my models are accurate to begin with? So these AI may be as better because they are more accurate. How to convert the black box into white box with the physics laws? Sometimes we don't necessarily need rigorous, sophisticated equations. True. Actually, sometimes we overdo it in developing equations that are hard to implement and models that are hard to be useful. So we are guilty of that too. Let's stop here and allow for questions if there is time. Thank you.